Okay, so it's me again. I'm sorry, I know that you have been seeing too much of me already, but last time, I promise. Okay, so this time it is more about opportunistic networks, and it's actually part of the work which Asanga already presented in the OOPS simulator, in the OOPS framework. And it is concentrating on how actually to simulate or how to model users. So what is the problem? If what we're doing right now, and I can boldly say probably also you're doing exactly the same, is that the user is either something which you simply assume that it's there, but you don't really model him or her. You have a mobility, which is assumed, of course, to kind of move this user, but you imagine it kind of a, like somebody just moves you. And on the other side, there is the application which gives you data, again, to that virtual user, and everything kind of gets into the user as in a black hole, and nothing comes out of this user again. Which is not very realistic assumption, because we consume the data. When you read a message, you typically do something with this message. You delete it, you forward it, you like it, you dislike it. And depending on the context of the application, there might be even some other resulting actions, for example, running away. If you get a message which says fire in the building, you don't continue strolling around in your GPS trace, which was before, but you should probably run away. And if you consider, because those are actually also exactly the application scenarios for opportunistic networking, where you're trying to see how people are moving and how to exchange data while they're moving device to device. So there is a huge difference whether I'm always moving according to some model like SWIM or GPS or whatever else, or I actually react to the message I received, everybody runs away. So what happens in the network is that I have a huge gap. And this is, from a perspective of the network, an extremely big impact. So in this work, we are trying to give to the user back the control over the mobility. She should be able to use her feet to run away. And on the other side, you should be also able to do something with the application, to react to the messages, to save some of them, to ignore others, not to read some of them completely. So the goals are actually two. We'll make the users react to the messages, and in order to make this reaction possible, plausible, and realistic, we need also to give to the messages a meaning. So you cannot just say data packet 1, data packet 2, and this is the size of it. You have to give a meaning to that data. You have to give them back what is it actually. Of course, you shouldn't be exaggerating, because otherwise the scalability again brushes everything. So in order to explain you the model which we came up with, I need to do some definitions. So what is the user? The user can be defined mathematically, analytically as a tuple of the following components. First of all, there are some interests. I can define them myself. I can define them with some randomized models. It actually doesn't really matter. I can say things like I like theater, cinema, and cooking. Somebody else likes hiking and sports. Okay. They're simply some keywords which you put there. You also have the possible reactions to the messages you read. Those are, of course, application related. But for a given application, for example, do you know the application Yodel? Who knows Yodel? Okay, at least my group, thank you. So Yodel is a kind of a hype application currently running around the campuses here, mostly in Germany, where people exchange mostly jokes and kind of philosophical statements like it's too early in the morning for a beer. Is it or is it not? And there is no meaning to that, to those messages, but the reactions are clearly defined. You can like it, you can delete it, you can vote it up and down, and you can save it, which means that I would like to keep that joke because it was so great, I would like to read it next time to my friend. These are the possible reactions from the perspective of the user. This is all I can do with this application with these messages. Nothing else is allowed because the app is actually prohibiting me. What else can I do? There is also something which we call the base probability of reaction, which means that how active is this user in actually interacting with the application. When I use Yodel, I actually don't use it. It's installed, and if I open it up, it will be only for a couple of minutes every couple of weeks. I will scroll the first 5, and I'll go like, oh, students talking about nonsense, and that's it. I will not vote anything up or down. I just skim a little bit and ignore completely. This is my way of reacting to the messages. There are some students who vote down and up each individual message. There are thousands of those coming every day. Okay, so this is what we're calling the base probability of reaction. This is my tendency of interacting actually with the messages at all. And how much of those, how much I will react with which reaction to which of the messages. I will go into details later, it will be easier to understand. What is a message? The message is similar. It also can have keywords. For example, this is about a cinema which will be outdoors on Thursday evening in Bremen. Okay, that could be, for example, such a keywords. The keywords will be cinema and outdoors. That's it. What else is there is the so-called popularity. For some of the messages, you need to put some information to model it actually, to say how good is this joke, with other words. I cannot get that from the model itself. I need to say this is a great joke, and how will great jokes propagate, and how will be the dumb one propagating. And obviously, very few of the messages have a high popularity, and very many are rather dumb. Okay, this is something also extremely important in these networks. What else is some of the messages have also, exactly as I said with the cinema and the outdoors, they actually have a time and address where there is something about events, there is information about events. Cinema in Thursday evening in Bremen and that address. So for that we have start time, end time, address, and address. Okay. Some others which we also would like to model are the emergency messages. They also will have a start, end, and an address. For example, fire in this building. And for each of the emergency messages, I need also to define a radius in order to tell pretty much the people and the application how much affected are you. If it is something small, like a car accident, it's something very localized. 20 meters around, it's relevant, later not really. If you have something like an earthquake, you might want to put this radius to more than 10 kilometers because everybody is affected and everybody should be warned. This is what we're doing here. Okay, so how does the whole model works? I have to lead you through all of the steps. First of all of the simulated users, let's imagine we have 10 simulated users so that it's easier. They first see, before we actually start simulating, they see all of the messages which we will ever send out in this simulation. It's kind of a cheating here. Before the simulation starts, and given all of this information and the definitions, and I will explain later how exactly, defines to which message I will react how. Okay, this is done simply for speed up. It is actually the same as doing real experiments exactly in the opposite way. If we decide to do an experiment here, and I will try an opportunistic networking dissemination to give you some of those messages. Then later on, I will give you a questionnaire where I will ask you if these 10 messages were actually everything which we send out. Did you receive them? Would you have liked to see them? For example, if you have missed one, you might say, ooh, that was actually exactly what I wanted to see. The rest which I saw was not relevant to me. So we're putting that computation or that survey in front of the simulation, so for speed up, so that later we can simply use this information throughout the simulation. Okay, once we're done with that, okay, we have now to to first solve the problem how to calculate this reaction. So you remember we have messages and we have users. The users are identified by some keywords, interests, by some base probability, how much do I react at all, and by the reactions themselves. The messages have keywords, have popularity, and have something like start, end, address, and radius. So in case I don't know anything about this message, it's a yodel message, it's a joke. There are no keywords. It's nonsense to put keywords there. What we have here is an example of this yodel application over a whole weekend. And we have observed what was the reaction probability of people. That was something like 10,000 different jokes, mostly bad ones. And people to 90% simply did not react to those messages. They didn't do anything. You can get actually all of this data directly from their API. Some of them commented or voted, up or down doesn't matter. They commented or voted on these messages. And very few, it is 0.5%, actually saved them. That's it. So this information now can be used to calculate what is my reaction or the reaction of a simulated user, given the fact that we don't know anything else about this message. So the message is a joke, all of the other fields are simply set to null. So what I do is that the possibilities are that much, I will ignore it. It's not scaled correctly for better readability. With 90%, I will ignore it. With some 19.5%, I will comment or vote. What I vote now doesn't matter. It's simply the reaction which matters. And then with some very small probability, I will actually save this message. And so what I do is that this simulated user simply throws a dice between 0 and 100 with those probabilities. And I simply say, ignore, 90% will simply ignore it. That's my reaction to this message. The second possibility is that this message actually had some popularity. So we actually know something about these jokes. We know which one is a good one and which one is a dumb one. Now the probability of reaction changes, because you should have bigger probability to like a good joke, or the really bad ones, of course, also fall into that category. They're popular. They're not necessarily good or interesting. They're popular. So the probability now changes. And how we decided to model this is simply to say, well, I will simply start with this popularity here. The popularity is defined between 0 and 100 itself. 100 means, even if you look into this model, that I will actually have only one possibility to save it, if the popularity of this message is 100. If it's something less, if it is 0, it is the old story here. And something in between, I simply remove some of the probability of ignoring it. And everything else, I give it now, I'm shooting, with other words, at this interval here only. Again, with a random number. So now, for some more popular messages, I have much bigger probability to say something else and not to ignore it. And the third possibility is that I actually not only have popularity, but also keywords. If the keywords are matching, the more keywords are matching, and the more the popularity is, the smaller gets this interval again, where I can actually select one of my reactions. So if everything matches very, very well, but maybe not to 100 yet, I will have some possibility to say comment or vote, and the rest will be to save it. So I will react much more stronger to something which is very popular and matches all of my interests. That's the whole model, actually. How do we use it then? Okay, now we start actually the simulation. All of the users know now for which message, which reaction should they produce. The message assume now you receive a real message. You first check whether this message has a start or end timestamp, and whether you have received it on time. If you have received it on time, you continue here later. if the message arrived after this end timestamp, you get angry. You missed a message. It's too late to get it. We set something which we call the angry bit, and we always react with delete and ignore, because you're actually really angry about these messages. You don't like them, you delete them immediately. If that was not the case, you look up what was actually your originally predefined or pre-computed reaction. Let's say it was safe. It was very good. So here the next question to ask is, was that the maximum possible reaction? So was it a safe, or was it rather something in between, like ignore or vote or comment or something like that? It was the highest possible. Then I have to ask the question, is that actually an emergency message? That is managed directly by the application. That's defined actually by the model, that the emergency messages where you are in the radius, you always react with the most strong reaction you can think of. That's in order to force the network to propagate this message, because it's an important one. So if that was the case and you have an emergency message here, then you have to ask the question, am I around? And if you are around, you should run, which means that you give now a signal to the mobility model to get you out of this radius. This is then handled by a special mobility model, which we're calling the reactive mobility models. I will come to that a little bit later. What happens if that was not the maximum reaction? It was a comment or a vote or something like that. Well, I can also ask the question, should I go to that event? Should I go to the cinema on Thursday? I randomly decide. If I decide to go, I give the message details, pretty much the address and the start time, to the mobility model, so that the mobility model will schedule for me that I'm going to that cinema on next Thursday. And it does it. Again, this reactive mobility model. If this is not the case and I decide not to visit this place or this event, or it was completely not eligible because it was a joke actually and not an event, then I simply wait for the next message to come in. This is the whole model. This is how the user now reacts, evaluates the messages which are coming in, and decides what to do. He can do something by simply pushing a button on the app, save, comment, ignore, or he can actually decide to do something with this message by saying, I would like to visit the party next Saturday, or I should run away because I'm in danger. Okay? So the next question is a little bit about these reactive models. The reactive mobility models can be any mobility model which is free to decide what are the next positions. With other words, I cannot use GPS traces because those are fixed. And we're working right now on another model where we will make it possible also with GPS traces to use parts of them only and to connect them in a more free way with each other. But right now, we're not able to do that. So right now, we can use any other mobility models. For example, SWIM is what we use currently. And you can put also random mobility. You can put whatever analytical model actually you would like to. Which means that this one simply has now to implement a small additional interface which says, bring me to that place at that and that time, and that's it. Or now out of this and that radius. These are two functions which any mobility model can implement, and then it's automatically a reactive mobility model. Another question to answer is, what could be now the parameterization of different realistic applications? I have been talking now about YODL application. This is one of our scenarios for opportunistic networking because they have lots of advantages compared to, let's say, a hosted application. First of all, people are free to exchange messages without any infrastructure, without any payment, and it's absolutely delay-tolerant application. Who cares when the joke will arrive? And if you don't pay for that, it's probably even better because all of the guests, all of the international students, for example, can much easily integrate into the app instead of needing always the internet connection. So in order to parameterize those, this is actually the example which we also have in the paper. We assume a good one will be 500 to 1,000 people on a campus, for example. There are no user interests, there's nothing like that. The user reactions are exactly what I have presented. Number of messages should be approximately 5 per day, not more than that. Those are already very active users. And traffic model, I have said Poisson. You remember the discussion of Asanga, that actually doesn't matter. With that low of a traffic, it might matter. That's why we decided here for Poisson. And the keywords, there are no keywords. The popularity of the messages is spread. The most popular ones are very few, only 1%, and they have a popularity of 50. So with 50% probability, you will react in some way to those. And the time of place, they also do not have that. Another very interesting application which we would like to serve are city events notifications. Exactly what I was saying before, cinema on Thursday, party on Saturday, coffee shop 10% off every morning, things like that. For that, you need to simulate the complete city and all of the people inside. Of course, only the users inside. So the number of users is approximately 2,000 to 10,000. We considered here the city of Buchholz, which is where Asanga is living. If nobody knows where it is, it's the city of Buchholz. We decided to make that famous. The user reactions are similar to those, but they are differently named so that it's clear what you actually do with them. For example, there is a possibility to save and go, or only to save. Save means that I was interested in that. I would like maybe to say to somebody else, but I'm not planning to go. And for some very few events, you actually schedule to go there. It's like putting them into the calendar. You have very low number of messages per user, extremely low. How often do you know about something happening in the city? Traffic model is again Poisson for the same reasons. You have some user interest this time, user and keywords. It could be sale, concert, exhibition, outdoor, food, and so on and so forth. It doesn't really matter. You should not exaggerate with the number. The popularity of the messages is similar, and place and time is also something which makes sense simply. And the third application which we're targeting is the emergency notification, very important. Again, very large networks, no interest or something like that. The user reaction is one possible run. The only thing which makes sense. Again, extremely low number of messages. This actually doesn't matter anymore. It shouldn't be continuous traffic anyway. We pretty much imagine it more like a one emergency message which interrupts everything else, and it happens very rarely at different places. Poisson exactly the same, but exactly as I explained already. And the popularity of the messages is 100%. So you always react with the maximum reaction days, and there is nothing else actually to go. Time and place of the messages should be completely random because you never know where the emergency comes out with. The implementation in OMNeT is not that complex actually. What we have here, this is part of the OOPS framework again. We have here the application, the forwarding, and the link, which are part of OOPS. We have here the reactive mobility and the user behavior model. And here, I just wanted to say also, we have actually two different versions of those. We can have the user behavior model, which is without mobility. So I only push the button on the app. It's also an important step forward already. Then I can use my old mobility models, whatever they were. Or I have the full-fledged version where I also run and schedule my events. Then I need a reactive mobility here. That's all. So what are the next steps? We actually need to validate this model with real users. And my question is, can we contact you for some questionnaires at some point? That will be very helpful to us, but I will bug you even if you tell me no now. So don't worry, I'll come back. Thank you very much. Any questions?
I think we have time for a couple of questions.
I'm not sure how can I understand the relationship between popularity and the user reaction? Because slides number, I think 11, you changed the or discarded lower end of the user reaction. Am I right? Yes, this one, the second part.
This one.
Yeah, for example, popularity is 50, and then you just simply discard 0 to 50. So this is actually kind of the change of the certain distribution.
Yeah.
What is the justification behind this specific?
Okay, this is exactly the point which we need to validate actually with real users, how exactly the distribution changes. This is the first guess, and the explanation for that is the following. If I give you a joke and I tell you this is a good one, you will rather read it. Okay, this is not exactly what we're trying to do here, but that's the explanation. If by default I know or I stamp this joke as good, and if I give it to everybody here, assuming it's really a good joke, then the probability of each of you to react more strongly is bigger. That's why the distribution is changing. There is still some residual probability that you will ignore this joke. It depends on the popularity of the message. If it is one of those which go viral, everybody will love it. Which one goes viral? Emergency messages. Those goes really viral.
The reason I'm asking you this question is that because you use the probability to model, for example, this reaction. So first one is that I'm not sure how you model or measure this usual reaction, ignore, comment, and then save. How do you measure, for example, 90 and then 9.5 and then 0.5 is like this? This is independent of popularity when you measure or something like that?
Yes.
So this first A part is nothing to do with the popularity, but once we know the popularity of the message, then this usual reaction would be changed, am I right?
Yes.
This is something unclear to me because when we're talking about the probability, this event A and event B is independent each other, we know that. But looks like this popularity and then the user response, these two events looks like a very closely related, dependent.
They're not dependent, they're completely independent from each other. Let me give an example.
Completely independent, you mean?
They're completely independent. You and me have a different base probability. This is my base probability. With 90%, I will ignore the message. With 10%, I'll do something else. For you, the base probability is 50-50. Okay, with only 50%, you ignore your messages, and with another 50, you do something. Let me simplify that simply, okay? Then on top of that now comes the popularity of the message. This one message comes to both of us. And this message is stamped as a good joke. The popularity is 50. Okay? Now my distribution will change exactly to this case here. With the residual one is 50, and I will have exactly this distribution to react to this message. Your, if you remember, was only 50% ignoring the message. So now yours will be cut here, and you will have only those two options, command or save. So those are they're on top of each other. We might need to discuss it in the break with a little bit more details. But as I said, exactly what are the values of the distributions, this is something which we need still to validate very, very much. The base probability comes from this experiment over 1 weekend with the Yodel application, but it's only 1 weekend.
At the time, you didn't take into account the popularity when you measured
No,
about A.
no, no.
Okay, so maybe thank
Yeah,
you,
thank you,
Anna, for the presentation. We can very interesting one. We can continue with the question afterwards.